Relativistic momentum is defined like non-relativistic momentum as the product of relativistic mass and velocity. So P equals mv equals gamma v m naught v, where gamma v is a function of the speed v of the particle. In four-dimensional spacetime, we can define a displacement 4 vector as follows. C delta t, delta x, delta y, delta z are the four components, which can be written as c delta t and then delta r, where delta r is the space interval with its three space components. The first component is called the time-like part, and the three space components are called the space-like part. The invariant space-time interval is calculated from the displacement 4 vector by squaring the time-like part and subtracting from it the squared magnitude of the space-like part. In a similar way, the form momentum is defined as mc for the time-like part and the relativistic momentum for the space-like part. Note that the three-dimensional relativistic momentum p is not the same as the four-dimensional form momentum, but is a part of it. Consider a particle of rest mass m0 moving with velocity v in frame S, where v is not necessarily in the x direction. In frame S, the particle has mass m equals gamma v m0. Just as the spacetime displacement 4 vector has an invariant interval, so does the form momentum, calculated in the same way by squaring the time-like part and subtracting from it the squared magnitude of the space-like part. Because it is invariant, its value is the same in S and in another inertial frame S', in which it has mass m' and speed v'. Recall that S' moves with speed u in frame S along the x-axis. So m' squared c squared minus p' squared is equal to m squared c squared minus p squared. Now let's look at the special case of the particle at rest instantaneously in a frame S'. For simplicity, we keep standard configuration by placing S' like this, with v in the x' direction, and shifting and rotating S to line up like this. The particle is instantaneously at rest in S', even if the particle is accelerating. Frame S' cannot be accelerating because it is inertial, but for our analysis, it is sufficient that the particle is at rest in S' just for an instant. In this setup, in S, the particle and frame S' have the same speed, so v equals u, and in S', the particle has rest mass m0 and speed v' equals 0, so p' is equal to 0. Then the invariant interval in S' is m' squared c squared minus p' squared, which is equal to m0 squared c squared. Since this is invariant, it is equal to the interval calculated for frame S, so m0 squared c squared is equal to m squared c squared minus p squared. The same result can be obtained without using a 4 vector and its invariant interval. Start with m squared c squared minus p squared, which is equal to m squared c squared minus mv squared, which is equal to m squared c squared minus m squared u squared, since v equals u in this case, which is equal to m squared into c squared minus u squared, taking out a common factor m squared, which is equal to gamma m0 all squared, since m equals gamma m0, times c squared minus u squared, and then that is equal to gamma squared m0 squared, and then c squared into 1 minus u squared over c squared, where we've taken out a factor c squared. We recognize 1 minus u squared upon c squared as 1 upon gamma squared. So we have gamma squared m0 squared c squared multiplied by 1 divided by gamma squared, which is equal to m0 squared c squared, which gives us the same result we obtained previously. This may be rearranged as m squared c squared equals m0 squared c squared plus p squared, which is the starting point for looking at relativistic energy. Multiply this expression by c squared to obtain m squared c to the power fourth equals m naught squared c to the power fourth plus p squared c squared, or mc squared all squared equals m naught c squared all squared plus pc all squared. Now the quantity mc squared has the dimensions of energy. For example, classical non-relativistic kinetic energy at speeds low compared with the speed of light has dimensions of mass times speed squared. This leads to defining the relativistic energy as E equals mc squared, which is equal to gamma v m naught c squared. For a particle at rest, P equals 0, so the relativistic energy is the rest energy E naught equals m naught c squared. This means that mass is a form of energy, so a particle with mass possesses energy due to its rest mass alone, without motion. With these definitions of energy, the invariance interval can be written as E squared equals E naught squared plus P squared C squared. We can define the energy momentum 4 vector as C times the 4 momentum. So C times mcp is equal to mc squared pc, where now the time-like part is the relativistic energy and the space-like part is momentum times c. This has invariance interval m squared c to the power fourth minus p squared c squared, which is equal to m naught squared c to the power fourth for a particle in its instantaneous rest frame, which gives us the result found previously. The energy of a moving particle is E equals gamma E naught, which consists of its rest energy plus its relativistic kinetic energy, defined as K equals E minus E naught, which is equal to gamma minus 1 E naught, which is equal to gamma minus 1 times m naught c squared. Now, the relativistic kinetic energy corresponds to the classic non-relativistic kinetic energy for speed v very much less than the speed of light c. In this case, K is equal to gamma minus 1 times m naught c squared, which is equal to 1 minus v squared upon c squared to the power minus a half minus 1, all multiplied by m naught c squared. And now we use the binomial theorem to approximate 1 minus v squared upon c squared to the power minus a half as 1 plus half v squared upon c squared, and then minus 1 times m naught c squared. So 1 minus 1 cancels, and we are left with half m naught c squared times v squared upon c squared, which is equal to a half m naught v squared. This is the non-relativistic kinetic energy K, which demonstrates the proposition.